Bismillahirrahmanirrahim. In the previous two lectures, we have developed a new model for time branching probabilities and shown how to calculate with it. In this lecture 8C, we will show some applications of these models. The first application is to create a simple model for a sequence of weather events. We will consider only two events, rainy or clear. Here is a very simple hypothetical model of 2 days of sequential weather. Here we create a very simple hypothetical model of 2 days of sequential weather with only two events, either rainfall or clear. So on the first day, there is a 20% probability of rainfall, which we call 1R, and there is an 80% probability of clear weather. So given 100 potential days, 20 of them will be rainy and 80 of them will be sunny. So now suppose that rainfall occurs. Then on the second day, there is a 30% probability of rainfall. So that's because we are showing a pattern of dependence where the second day weather depends on the first day, and rainfall is more likely following rainfall. On the other hand, a clear day, instead of having 80%, now only has 70% probability. Similarly, if it is a clear day, then there is a bigger probability, less probability of rainfall. It's only 10% now, and a higher probability, 90% of being clear. So basically, we have dependence. If there is rain, then it is more likely to be followed by rain, and if it is a clear day, it's more likely to be followed by a clear day. If you track what happens on the 80 and 20 potential days, you find that there will be 6 days in which both days is rainfall, 14 days in which you have rainfall followed by clear weather, 8 days in which clear is followed by rain, and 72 days of clear weather on both days. So these are very simple probability calculations which can be made by just using the probabilities. The mathematical notation to show what is in the diagram is very awkward. That's because we have time-dependent probability. At what time are we evaluating the probability, and what is the timing of the event? Both of these things need to be mentioned. So here is the notation: probability at t equals 0 of rainfall on the first day is 20%. So if we just want to simplify this, we can say that if time is not mentioned, then time is 0. And 0 is, again, by convention, a time at which nothing has happened. So all of the events occur after t equals 0. So here we can say that this is probability of rainfall on first day followed by rainfall on second day. And since there is no mention of time, so it's the probability is at time equals 0. Now consider a second probability. What is the probability at time equals 1 of rainfall on the second day? Now this is a problem because this probability cannot be evaluated, because the probability depends on rainfall or clear, and on the first day one of these two events has happened. So we have to specify what happened on the first day in order to be able to tell the probability of rainfall on the second day. So here is the correct notation: probability at t equals 1 of first day of rain followed by second day of rain is 30%. So this notation specifies that if we are talking about probability at t equals 1, then rainfall occurred on the first day. So with this complicated set of notations, we can now write what is a very simple formula in a standard probability theory. So if I want to calculate the probability at time equals 0 of rainfall on both days, then I have to write this as probability at t equals 0 of 1 rain followed by 2 rain. So now this is the probability at t equals 0 of rainfall on the first day multiplied by probability at t equals 1. Now we move to time equals 1 and we ask what is the probability of rainfall on the second day given that rainfall occurred on the first day. So this is 20% in the first day of rainfall and then 30% on the second day if it has rained on the first day. So multiplying these two, 20% times 30%, we get 6%. We can compare this with the standard notation, which is that if you have probability of two events, A and B, then the probability is probability of A times the probability of B given A, and also it can be written as the probability of B times probability of A given B. There is no time sequencing. You can condition either event on the other one and multiply by the probability of the one event. There is no time sequencing involved. This in our notation is wrong. We have already written the formula for this in the previous slide. Time reversal cannot be done, and basically the Bayes formula, which is a very famous and controversial formula, does not hold in our framework because time sequencing cannot be reversed. One very important special case occurs when the 2 days are independent. So in current situation, the probability at time is equal 1 that rainfall occurs on the second day is 30% after rainfall, and it is 10% after a clear day. So these two are different, and that means that the probability, what happens on the second day, rainfall, depends on weather on the first day. Now independence holds when both of these probabilities are the same. So probability of the second day of rainfall is fixed regardless of what happens on day 1. In this case, probability of rainfall on the second day followed by first day rain followed by rain, or first clear followed by rain, both of them are the same probability, and so we can talk about probability of rainfall on the second day at time equals 0 without mentioning what happens on day 1, because what happens on the day 1 does not affect this probability. So in this case, if I want to find out what is the probability of rainfall on both days, I can compute separately the probability of rainfall on the first day and the probability of rainfall on the second day and multiply them. So this is the very important special case of independence, where in calculating the probability, I don't need to say what happened on the first day in order to compute the probability of the second day. And so we can say also in simpler notation that probability of first day rain followed by second day rain is the product of these two probabilities. So how will we know which model should be applied? Well, there is empirical evidence which is based on past rainfall data. We can see how often rainfall follows rainfall and how often rainfall follows a clear day, and see if these proportions are the same. So that's empirical evidence. We can also look at mechanical models of the weather. That is how winds, clouds, and atmospheric pressure contribute to rainfall. And then using these models, we can see how often whether the second day events are dependent on the first day events. And both types of information are used in constructing probability models. As a second example of application of time branching probability, we will explain the base rate fallacy, what it is and why it occurs. So this is commonly used in detection of any disease, but breast cancer is a common example. So base rate is the general prevalence of breast cancer in the population. So suppose that 10% of females in a high-risk age group, let's say from 50 to 70, have breast cancer. Screening is a simple test for detecting this, and it detects 95% of the cases in which females have breast cancer. So the sensitivity of this test is 95%. Suppose if a woman has cancer, it will be detected with 95% probability, 19 out of 20 women. But also, all tests have false positives. Some women who are screened are shown to be positive, even though they don't have breast cancer. So let's suppose that there is false positives in 10%, which means that 10 healthy women, out of 10 healthy women, one of them will show signs of having cancer. So, so now we ask the question. This is suppose that a woman goes in for screening. What is the chance that, and it turns out positive, what is the chance that she has cancer? So this question often leads to large amounts of answers which are wrong according to the pre-experimental probability theory, and this has caused a lot of confusion, and it has caused accusations that human behavior is irrational. But we will see that this is not so. A time branching T diagram makes clear what the issue is with base rate fallacy. Remember now that all of these calculations we are going to be made are pre-experiment, pre-screening. So in a population of 1,000 women, 10% have cancer, that's the base rate, and 90% are healthy. When they are tested, then suppose that 95% are tested of the cancerous women, 95 are positive, which means that 95 cases are detected, 5 are missed. Among the healthy women, 10% of them come out with false positives, so there are 90 positive tests. So we see that both of them are roughly the same, 95 to 90, which means that if a woman tests positive for screening, the chances of her having cancer are only about 50%. If you change the base rate from 10% to 1%, then only 10 women have cancer in the population and 990 do not. So there will be about 99 positives from the healthy women and 10 positives from the women with cancer. So the probability of cancer, if you have a positive test, will only be 10 out of 99, or only around 10%. So there is a huge number of false positives. So the base rate makes a huge amount of difference, and people when they are asked what is the chance that a woman who tests positive for cancer, do not usually factor this base rate into account, and this is said to be a fallacy. What I would like to argue here is that this is not a fallacy, because once you have obtained a screen test, a woman comes in, she has tested positive, then the probability no longer applies. The probability of a false positive was true for the population in general when you were going to select some woman at random to test. Now that a particular woman has been selected and she has tested positive, should we consider that a random woman who was selected would have 10% or 50% probability of being positive? This is not really relevant. The probability is not an issue. This is now a question of confidence. How much confidence can you have in the test? Well, this confidence can vary, but it doesn't really have to do with probability. And the main issue that will face us is that now this woman has tested positive. Should we disregard this evidence, or should we go for further tests? Obviously, now that that there is a particular woman in hand, she should be tested further. Another way to think about it is that this woman, which we have, is maybe 57 years old. Maybe she is Latin American. maybe she has blonde hair. All of these characteristics create different groups in the population, and these groups will have different base rates. So the point is that the base rate no longer matters because we have a particular woman in hand and she has tested positive. So what would have happened in general to some random choice is not relevant, and this is how people reason intuitively, whereas statisticians are used to doing pre-experimental reasoning and they consider that to be rational, and that's why this is called the base rate fallacy. As our next example of use of time branching probability models, we consider the issue of sun preference. The populations in countries display sun preference in the sense of that there are more young children who are males than young children who are females, even though the probabilities of birth for males and females are very close to 50% almost universally. So what accounts for this differences in gender? So to understand this, we consider an artificial problem. Suppose that in a country, people want to have one child, one son, and so they keep having children until they have one son. So in 100 families, there are 50 of them will have the son and 50 of them will have a girl child, and so the 50 who have sons stop and the 50 who have girls go on to try for a second child. So among these 50, then 25 sons will be born and 25 girls will be born, and the families with 25 sons will stop and those with 2 girls will continue, and at the third stage 12 sons and 12 daughters will be born, and so this keeps on going. But notice that at each stage we always have balance between girls and boys. So even though people prefer sons, they are trying to get one son, this stopping rule does not lead to gender imbalance. Regardless of what stopping rule they use, if they want to get 2 sons or 3 sons and they ignore girls, or whatever they do, just by changing how many children they have, they cannot change the ratio of the genders. So we see huge imbalances in female and male children. So what accounts for that? One thing we understand is that our probability model shows us that it cannot happen just because people stop having children after having sons, or they want to have a particular number of sons. So the only thing which can cause differences is if there are abortions, if female children who are fetuses are aborted, or if there is inequitable health care, if the young children who are females don't get good health care and they die, and and young infants who are boys get much better health care, much better food, nutrition, etc. As our last example, we consider a very famous problem, which is about a game show in which you're trying to find where there is a car behind a door or not. And this problem has caused a huge amount of confusion. A large number of top mathematicians and physicists don't agree with the standard answer, and the standard answer is supposed to be very confusing and puzzling. So we will discuss both what the standard answer is and why it is wrong and why there is so much confusion about this. So here's the standard analysis of the game. There is a game show in which you are standing in front of 3 doors. One of them is goat and 2 is goat and the third is a auto, and you get to choose one of the 3 doors. You choose one door at random. There's a 1/3 probability that it is the first door which has a goat behind it, and a 1/3 probability that second door which also has a goat, and a 1/3 probability that you choose the right door, which has the grand prize of the automobile. Now, after you choose the door, but before you before you know what is behind the door, the host offers you a choice. He takes one of the doors you did not choose and shows that there is a goat behind it and asks you if you would like to switch. So if you have in the first option you chose door 1 which had a goat, door 2 also has a goat, so host shows you the door 2 and asks if you want to switch. If you chose door 2, then he shows you door 1 which has a goat behind it and asks if you want to switch. And if you choose the third door, then the host reveals either the first or the second door, both of them have goats, and asks if you want to switch. Now what happens if you switch? You have to decide whether or not to switch. So in the first option, if you switch, you get to the automobile. In the second option, if you switch, you get to the automobile. But in the third option, you get a goat. On the other hand, if you don't switch, you remain with your goat in the first option, you remain with your goat in the second option, and you remain with the goat in the you remain with your automobile prize in the third option. So if you don't switch, you have a 1/3 probability of winning the automobile. But it seems that you should switch because in 2 cases out of 3, you win the automobile by switching. However, this is one model, one probability branching model, but there are other models which you can apply which lead to different results. So there are actually 2 problems with this analysis. One is that there is a this analysis fails to differentiate between probability and confidence. After you have chosen the door, the host knows whether you have chosen the automobile or the goat, and this knowledge must be taken into account because there is no longer probability. Whatever probability was there before you made the choice, but it does not exist after you made the choice. So the question should be thought about in different ways. You have to think about, now you know, the host knows, we have to think of the game from the point of view of the host. The host knows whether or not the contestant has chosen the automobile or the goat. So now what should he do? This is the key question. So here is the alternative model. You are at one of 2 branches. You have either chosen the goat or you have chosen the automobile. There is no probability anymore. Now what happens going forward? The host can, if you choose a goat, the host can just open the chosen door and reveals the goat and says, okay, sorry, you lost. You chose the goat and you get the goat. Or he can offer you an option. If he opens the other goat and offers you an option, then if you switch, you will win the auto, and if you don't, you will get the goat. So the only way for you to win an automobile in the case that you have chosen the goat is if the host offers you an option. In that case, if host offers options and you switch, then you will get the goat. Then you will win the auto. Otherwise, you lose. Now, in the other case, if you have chosen the auto and host offers you no option, host can just open the door and say, congratulations, you made the right choice, you won. Or he can open a different door, and both of the doors now have goats, and he can say, okay, here's a goat, do you want to switch? If you switch, you will get the goat, and if you don't switch, you win the auto. So this is the picture of the deterministic game where there is no probability. It's just a game of strategy. So the question is, what should the host do? Well, it depends on what the host wants to do. But in general, the host is playing against the contestant. He wants to force you to lose. So in the first option, he will offer you no option. And when you have chosen the automobile, he will try to psych you into switching the gates. So this is very much aligned with the idea that he will offer you no option if you choose the goat, but he will offer you an option and hope that you make a mistake when you choose the automobile. So there are these 2 models about how we should think about the game. So how should we decide? Again, there are 2 two ways to look at it. We can look at the reality, the empirical evidence. So there is a famous movie called Slumdog Millionaire, in which the host first chats with the contestant to build up trust and to say that, oh yes, I'm like you and I want you to win. And then he gives him the wrong hint in order to try to make him lose. The same thing happened with Monty Hall, who was the contestant in the original game show from which this puzzle is taken. And he talks about how he can deceive contestants into switching their choice even when they have chosen the automobiles. And he demonstrated by playing 8 games. In all of them, the contestants lost because when they chose the goat, he revealed the goat, and when he chose the auto, he would psych them into switching. So the question that we need to ask is the host choice of strategy. Host knows whether or not you have won. So if the host, what is the host trying to do when he offers you the choice? Is he trying to make you win, or is he trying to make you lose? If you have chosen the goat, then the only reason for the host to offer you a choice is if he wants you to win. But if you have chosen the automobile, the only reason for the option is if he wants you to lose. So it's all a question of psychology. What is the host trying to do? Host who knows what you have chosen is trying to do. So again, this is a question of psychology, not of probability, because we are in the post-choice world. All of the probabilities apply to the pre-choice world. The goal of this lecture was to explain how we make and use time-branching probability models. These models clarify many confusing probability calculations. A lot of confusion exists in the world because people do not differentiate between pre-experimental probability and post-experimental probability. So probability that x equals head is 50% is written in textbooks, but it is never explained that this is true before the coin is flipped, but not afterwards. So some general philosophical remarks on time branching probabilities. Here we stand at t equals 1. There are 3 options. Now, in a time branching probability world, there are many forks and many branches, but only one of them will be chosen. The other alternative will disappear. So suppose that at time equals 2, the one option that occurs is the one that is real, and the all others disappear from the picture. So these were things which might have happened but will never, which are just non-existence as possibilities. And similarly, as we go down the branches, the options that existed before that time will disappear after one of the choices occurs. So we keep moving in one particular world, but lots of possible worlds which could have been but never were will be there, almost there for us to grasp. But when we make the wrong choice or made the different choice, we will enter into a different world. So this is a very radically different picture from the picture of deterministic worlds which we have been trained to believe from the Newtonian laws of deterministic motion.